लोग अक्सर कहते हैं कि ये है नया इंडिया, लेकिन ऐसी क्या खास बात है नए इंडिया में? शहर भले ही छोटे हों, ख्वाब बड़े ही बनता है नया इंडिया। अपने हाथों से अपनी कहानी खुद लिखने का दम रखता है नया इंडिया। नए इंडिया की सोच में सबको बराबर अधिकार है। मेहनत के बीच से सफलता की मुस्कान तक, हर सफर में एक नए मुकाम तक, नई ऊर्जा, नई उमंग से चलता है नया इंडिया। नई उम्मीदों के साथ तरक्की की राह पर आगे बढ़ रहा है। अपनी कोशिशों से आसमान की बुलंदियों को छू रहा है। इस नए इंडिया के कण कण में, इसकी हर धड़कन में बसता है नए इंडिया का नयारा।
उगती हुई हरियाली में, सोने सी हर बाली में, हर सुबह चाय की प्याली में और घर घर की खुशहाली में, प्रदूषण मुक्त हो आसमान, दुनिया भर में अपने निशान, आत्मनिर्भर हिंदुस्तान, खेल इंडिया जिसकी पहचान।
लोग अक्सर कहते हैं कि यह है नया इंडिया, लेकिन ऐसी क्या खास बात है नए इंडिया में? शहर भले ही छोटे हों, ख्वाब बड़े ही बुनता है नया इंडिया। अपने हाथों से अपनी कहानी खुद लिखने का दम रखता है नया इंडिया। नए इंडिया की सोच में सबको बराबर अधिकार है। मेहनत के बीच से सफलता की मुस्कान तक, हर सफर में एक नए मुकाम तक, नई ऊर्जा, नई उमंग से चलता है नया इंडिया। नई उम्मीदों के साथ तरक्की की राह पर आगे बढ़ रहा है। अपनी कोशिशों से आसमान की बुलंदियों को छू रहा है। इस नए इंडिया के कण कण में, इसकी हर धड़कन में बसता है नए इंडिया का नयारा।
उगती हुई हरियाली में, सोने सी हर बाली में, हर सुबह चाय की प्याली में और घर घर की खुशहाली में, प्रदूषण मुक्त हो आसमान, दुनिया भर में अपने निशान, आत्मनिर्भर हिंदुस्तान, खेल इंडिया जिसकी पहचान।
लोग अक्सर कहते हैं कि यह है नया इंडिया, लेकिन ऐसी क्या खास बात है नए इंडिया में? शहर भले ही छोटे हों, ख्वाब बड़े ही बुनता है नया इंडिया। अपने हाथों से अपनी कहानी खुद लिखने का दम रखता है नया इंडिया। नए इंडिया की सोच में सबको बराबर अधिकार है। मेहनत के बीच से सफलता की मुस्कान तक, हर सफर में एक नए मुकाम तक, नई ऊर्जा, नई उमंग से चलता है नया इंडिया। नई उम्मीदों के साथ तरक्की की राह पर आगे बढ़ रहा है। अपनी कोशिशों से आसमान की बुलंदियों को छू रहा है। इस नए इंडिया के कण कण में, इसकी हर धड़कन में बसता है नए इंडिया का नयारा।
उगती हुई हरियाली में, सोने सी हर बाली में, हर सुबह चाय की प्याली में और घर घर की खुशहाली में, प्रदूषण मुक्त हो आसमान, दुनिया भर में अपने निशान, आत्मनिर्भर हिंदुस्तान, खेल इंडिया जिसकी पहचान।
Welcome back, ladies and gentlemen. We're about to resume shortly. All our delegates in the pre-function area, may I please request you all to kindly join us back in the hall. We're going to resume in the next couple of minutes, and we want your 100% presence in the hall. Thank you. Good morning, ladies and gentlemen. For those of you who've just joined us for this session, a warm welcome. We're just waiting for a few more delegates to join us. Sharp at 11:15, we shall commence the session. Until then, relax, enjoy. And don't forget to scan the QR codes to get your pictures. Pictures from all 3 days will be on your phone. All you have to do is scan this QR code and register your face. I was also asked if pictures from today will be shared. Well, it's not real time, but by the end of the day today, you will definitely have all the pictures of all 3 days. morning and a warm welcome. Welcome back after a short break. And this is the last session, the last technical session of this year's Energy Technology Meet. Now that we have you all here, may I please request for a round of applause? Everyone? I'm going to take this up a notch and ask you all if you've really enjoyed being a part of the last 2.5 days. I want you all to really show us, because a lot of people are involved in putting this entire event together. As a token of our appreciation, can we take a moment to put our hands together and tell them that this year, the 27th Energy Technology Meet was fantabulous. Come on, keep it coming, everybody. Keep it coming. This is a thank you going out to all those people who worked really hard in making this event a grand possibility. On that happy note, ladies and gentlemen, we have one last technical session to go. But before that, we have a surprise happy segment. Now, we have fantastic stalls here. I'm sure everybody's taken a look around the exhibition. And now we have this one moment where we will declare the best stall award or the best exhibition award. I'm sure you all are eagerly waiting to find out who is going to back the award. Are you? Are you eager to find out who's going to back the award? Yes? How many of you are feeling confident? If you're feeling confident, let's hear you all put your hands together. Fantastic. I love the confidence, but it's not going to be me who's going to reveal the awardees. I'm going to invite Mr. Gaurav Mishra on stage to talk about these awards and tell us who the winners are. Welcome on stage, Mr. Mishra. Can we hear a round of applause?
Hello. Thank you, Archana, for allowing me to take up your job for a moment. So, very good morning, everyone. So, reflecting on exhibition stalls at the CTM, I would say that we are delighted to have 24 exhibitors, all of them putting on spectacular efforts and wonderful show over the past 2 days, right? If you walk across the area, you will find the entire area is brimming with unmatchable energy, enthusiasm, and passion, right? So let's take a moment to a big round of applause for all of our exhibitors.
24 stalls in this very place. Even before we announce the winners, Mr. Mishra, I think they all deserve a big round of applause. So come on, make it count. Congratulations to all of you.
Since last ETM, we began one tradition, so recognizing the hard work and dedication of our exhibitors by giving them a best exhibition stalls, right? So I'm glad to convey that taking this practice further, we are having best exhibition stall for this ETM as well. So there was a team of seniors who are constantly examining each stall independently on various factors the way the stall look, the way the content shown, how they are delivering the content, right? So based on this, the committee has decided to give awards in 2 categories. Category 1 belongs to the single booth stalls. And in category 2, we are having stalls who are double size stall of 6 into 3 meters. So without further ado, I take a privilege to invite on the stage Madam Varsha Sinha, Secretary OIDB, and Sri R.C. Agrawal, EDCST, to present the award. Okay, now, so I'm coming up with the names, breaking the suspense. So award in category 1 of single booth stall goes to, any guesses? The winner of this category is Chennai Petroleum Corporation Limited, CBCL.
Single booth winner for the year 2024. Ladies and gentlemen, come on, a thunderous round of applause as we congratulate Chennai Petroleum Corporation Limited.
Okay, now coming to category two, I must confess that there was a very tough competition. So there is a tie, right? So this award is jointly shared. So first, I would like to announce Engineers India Limited.
How about that? We have four winners. One of them being EIL, Engineers India Limited. Congratulations. Congratulations, Ms. Ghosh and the entire team. Can we hear a bigger round of applause, everybody? Put your hands together. Let's hear the celebration as we acknowledge the amazing contributions of EIL, the team that's here on stage. Double booth winner EIL. Thank you. Congratulations.
Okay, now coming for the second name. This award is jointly shared by, it is jointly shared by Topso.
Double boots winner Top So. Congratulations. Why are we not applauding? Come on, everybody. Let's celebrate the amazing win here. The Top So on stage, claiming their big win today. Double boots winner Top So. Let's hear it for Top So, everybody. Thank you so
everyone.
much for doing the honors.
Thank you, everyone. Thank you, Achana. Now dice is again yours.
Thank you, Mr. Mishra. What a beautiful moment that was. A moment for all of us. Really got celebratory. Can we take a moment to collectively celebrate all the winners here this morning? Everyone. Well, truly, ladies and gentlemen, the 27th Energy Technology Meet has been a fantastic, fantastic event. And with that, it's time for me to introduce to you all the last technical session for the year. Now, the last technical session, the topic is refinery performance improvement. And with that, I'd like to take this opportunity to invite our chairpersons on stage. Without further ado, please put your hands together and join me in welcoming Mr. Prasad Panikar, Executive Chairman, Naira on stage. Welcome, sir. Keep the applause coming as I invite Mr. Kaushik Singha, ED, PC, IOCL. Welcome, sir. And now, ladies and gentlemen, I'd like to take this opportunity to invite and introduce our eminent speakers who are going to be here on stage, and they will present their papers on refinery performance improvement. Without further ado, our first speaker coming onto the stage is Mr. Soumendra Banerjee, UOP LLC. Welcome, Mr. Banerjee. Please continue with the applause as I invite Mr. Dharmendra Kumar Narang from Technip Energies and Mr. Saneep Mahulkar from Reliance. Welcome, gentlemen. Welcome, sir. Our next speaker joining the dignitaries here on stage is Sandupti Bhutia from Indian Oil Corporation Limited. Welcome, sir. Put your hands together for Ms. Alka Sharma, Engineers India Limited. Welcome, ma'am. And last but not the least, ladies and gentlemen, Mr. Suhas Nair, Doff Kettle Chemicals India Private Limited, joining the dignitaries on stage. Welcome, sir. Once again, reminding you all, ladies and gentlemen, the last technical session of this year, and the topic of discussion is refinery performance improvement. All our distinguished speakers are here on stage to present their respective papers. So without further ado, gentlemen, over to you.
Good morning to you all. First of all, a warm welcome to my co-chair, Kaushik. I'm very happy to be back in the ETM, which we are meeting every year. More than the technology, this is an opportunity for me to meet all the colleagues from the industry, the technology suppliers, and also get insight about the new evolving technologies and also the modifications being done in our companies. So at the outset, let me express my gratitude to EDCST, RC Agarwal for giving this invitation. And also really happy that MOP and NG and this time along with Indian Oil Corporation is doing this event in such a big manner. Also congratulations to the various winners which we just concluded in the for the best exhibition done. Many of my old colleagues I was able to meet, including some of my colleagues sitting in the front row, and also I had the opportunity to meet my old boss, Mr. R. Ramachandran, ex-director refinery of BPCL, today morning. It was very nice. I'm sure that you all had a very fruitful, technology-packed discussion in the last 2 days. Even though this is the last session of this year's ETM, as our MC was talking, but it is extremely important and relevant in the current context. As we discussed today, all of you are aware that this topic we are discussing for many years. You know that I know at least for the last 30, 40 years, performance improvement of the refinery we are discussing in many forums. But it is slightly more relevant now. Why it is more relevant is we are just migrating from a double-digit GRM regime to a less than normal GRM. And the forecast is that we may stay in this for a couple of years, if not longer. It is very interesting that we have to wait for some refineries globally to shut down to create that higher demand and higher margin. not a good situation. But we have seen such similar issues earlier. And this group, the refining group, especially of India, is so resilient and capable that we will come out of all these issues very successfully. In spite of a lower margin, but there is one thing more positive is that still demand is growing. Then we need not unnecessarily worry about the margin, but it will come one day. But two or three factors as we speak is going to have a profound impact on our business. That I am talking about the refining business more than the overall the hydrocarbon industry. First is the regulatory compliance becoming stricter, nothing new. It will continue for many more years. But the important factor is we are going to have one more variable which we have to be extremely conscious while we operate our refinery. That is our carbon emission. So far, we were happy that we have no target on carbon emission. So we were happily monitoring our other emissions, sulfur or all type of other emissions. But carbon was never ever a target. As all of you are aware, from 1st of April 2025, as per the current information from Ministry of Power, that all the refineries are going to have a carbon intensity target. This is going to be a major change. If you are not getting it right, that we have to pay a penalty. The penalty in the form of carbon trading. We have to buy the carbon certificate, and also if you overachieve, then you will have a financial benefit. So carbon is going to be a factor which is have influencing your bottom line. May not be substantially to start with, but as we progress, it is going to be a major factor in many of the developed countries you would have experienced. So this factor is going to be the second one. I am very happy that some of our speakers are going to talk about the carbon, what are the ways forward to have some control on the carbon emission as we go ahead. But colleagues, also we know that we have substantially achieved, India as a refining industry substantially achieved in the last 30, 40 years. We have become a major global hub. We have got the best refineries in the world, and we are doing extremely good in the improvement process. We are participating in the global benchmarking, and our performances are good. All this we achieved because of the great people capability, the skill of our technicians, our engineers, the experience of the operating team, and the wonderful management team, and also the support given by the technological agencies, our own agency, Engineers India Limited, etc. So that people factor also is going to be influenced by the new tools available in the country. I am talking about AI. AI is not going to replace the job, but it is going to improve our productivity and our ability to perform better. So along with the carbon trading that is going to evolve, how we are going to successfully employ AI tools in our refining operation, in the optimization processes, and also in all other processes is going to decide how we are going to be successful, how we are going to be globally competitive. I'm very happy that we have got 6 number of very highly experienced and skilled speakers going to tell us on the various aspects of the refinery performance improvement. And thank you once again to be here. So my co-chair would explain to you the process. I think you must be familiar by this time. And after each session, we will have a Q&A. Request you to actively participate and get maximum benefit out of these deliberations. Thank you very much.
Thank you, Panika sir. A very good morning to everyone. It's a privilege and honor to be here in the last session of the technical discussions.
We have industry captains from multifaceted backgrounds and roles. And the last session is very, very relevant to the industry. And Panika sir has already outlined all the need and the importance of efficiency improvements and refinery performance improvement in the current context. So each panelist here will have about 15 minutes to make the technical presentations. The first technical session paper is on energy efficiency through low-level heat recovery and electrification. I request Somendra Banerjee from UOP to present the first technical paper.
Good morning. Am I audible at the back? Okay, so as this is the last session, I thought I will start with kind of my takeaways from the sessions that we have had so far. So which I feel is very important to this session as well. So I think we started on the inaugural day, we heard very significant comments about like our energy consumption will go up by 2.5 times from now to about 2047. So that's a significant increase. Then out of the global energy demand increase, I think 25% is being contributed by India, which is really another significant milestone. Our refining capacity from a current of 256 MMTPA will go to almost 450, which is 1.7 times. And as Mr. Panikar mentioned that we are already putting a lot of emphasis on energy recovery, on energy efficiency. And in fact, the EII, I learned that has come down by 19% as compared to 2010 to 2022 time period. So these significant things are being done. So it is not that, and Alokji started his comment with energy efficiency. So energy efficiency is very critical and significant things are being done. So the objective of this presentation is to bring forth to you the kind of things UOP is now bringing out to carry forward in this journey with you. So with that, let me, okay. I'll take reference to Dr. Maitra's presentation when he talked about the GHGs, the greenhouse gas. 6 of them, CO2 being the first one, methane, nitrogen oxide, and then the hydrofluorocarbons. Now, I stress on the hydrofluorocarbons because Honeywell converted these hydrofluorocarbons to hydrofluoroolefins. And when we convert them to hydrofluoroolefins, their GHG and ODP potential comes down. You will see how we have used that in our technologies going forward. So CO2, with a life of 400 years, is the molecule of focus right now, although methane, being much more potent than CO2, has a lower life, about 20 years. So the focus is there on methane, but I think the starlight is on CO2. And as again our session chair told, that pretty soon that carbon intensity thing will come. So we see a kind of different approaches around the world. Somewhere it is a mandate where you have to do it, mostly in Europe, where in US, by the Inflation Reduction Act, we see that there is an incentive. So ranging from $60 per ton to $80 per ton, depending upon whether you're sequestering or you are using it for enhanced oil recovery, and to about $160 to $180 per ton for direct air capture. So India definitely will come up with some either incentives or penalties for this. But the trend is, as has been published in different journals, this is taken from Bloomberg, that the CO2 price will keep on increasing. And we see that it is going to hit about $160, $170 per ton by 2035 or so. So there is an increasing trend. So it is no wonder that we are focusing on CO2 reduction, decarbonization. Okay. UOP has been developing technologies for our customers for what, 110 years now, discovering, innovating, and I think Mike in his session talked about the 6 efficiencies that we do, like carbon utilization, hydrogen, water, emission, utilities. All this together brings a lower capex and lower opex. So that has been a DNA of UOP developing technologies. So whether it is the process, whether it is the process equipment, as you can see, divided wall columns, hydrogen burners. Ranjit talked about a series of technologies UOP has for capturing CO2, whether it is from pre-combustion or post-combustion or PSA tail gases, so blue hydrogen. So we have a host of technologies. So we can capture CO2 from the flue gas, but the focus of today's my talk is on the green blocks that you see, is how to increase the energy intensity, how to take that heat which is generally lost to atmosphere. I think Mr. Prav Das said is the air condensers and the air coolers are just letting heat go to the atmosphere. So what we can do with that, and the tools of doing that, as you see, is electrification, one of them. So electrification is a major decarbonization drive, and India is also taking that much step ahead. Organic Rankine cycle, Ranjit mentioned about this in the organic Rankine cycle. This is not new, but you will see the differentiators that UOP has brought in to this. The heat pumps, we have been already using heat pumps earlier, but in a new way, how it has been integrated to the process, and mechanical vapor recompression, which is almost the same as a heat pump, but the fluids is different. You use steam instead of the process or any other fluids in this. So this diverse suite of CO2 reduction technology is already available, and we bring forth the new ones, and we would like to share that with you. Okay, so looking at the main 3 categories which we talked about is electricity. So why electricity? Electricity helps you reduce the scope 2 emissions, assuming that it will become greener and greener as time goes by. And it can also replace steam as a heating source in some of the process. It is possible, but we will see what the other considerations come. And hot oil system, as we consider in our LAB units. So can electricity replace that? And right now, if you see that our energy mix has a lot of coal in it, India has taken a lot of strides to get it replaced with solar. But as we go forward, is more drive. Since the electricity is green, it helps further in decarbonization. And low temperature heat recovery is the heat which we lost to atmosphere, mainly through this column overhead condenser, product rundown coolers. Can we use that heat somewhere else? If we use that heat somewhere else in the process, we are calling it a heat pump. You will see that indirectly or directly it is related to electricity. So a heat pump will need electricity to drive the process. So you elevate the heat using electricity. In the organic Rankine cycle, you use the waste heat and produce electricity out of it. So in a way, it is related to electrification of your process. And of course, if you are able to produce electricity, that much less you have to get from the grid. It kind of helps you to reduce your CO2 footprint, even though there may not be any credit on that electricity. This is just one thing to show you that how we see the electricity mix changing all over the globe. Although it's looked at US and Europe mainly, India is no laggard. India is almost now 42% renewable electricity in the mix. And as you can see right now, we are even higher than US. So going forward, this is expected to increase, and so is in our case also, our green electricity will go up. So right now, electricity, one may argue it has a high carbon intensity, yeah, because of the mix, because it is still you are using coal, you are using natural gas maybe. So as we go forward and we begin greener electricity, your carbon intensity will come down. And that is what this plot on the left shows, that by 2050, you see the CI coming down very low for Europe and US, and I'm sure for India as well. So process electric heating. I know Shreyoshi in her presentation yesterday talked about how we are trying to do this in a platforming unit. But it's not only platforming unit, and it is not new to EOP as such, because we have been doing electric heating for vapor phase heater across technologies. If you look at our Penex technology, platforming technology in the regeneration section, even for alkylation technologies, some of the hydro heaters, we have been doing electric heating of the vapor phase. Now we are extending it into even two-phase. That how can we go and start doing electricity for a two-phase thing, like a two-phase heater, a reboiler, where both vapor and liquid exists. Just to give you an idea, let us consider two examples, right? For example, a Penex unit or naphtha, light naphtha isomerization unit. You have finally a HP steam heater, right, to get to the reactor temperature because it's slightly higher. So when we are having a steam heater, your process temperature will never exceed the steam temperature, the steam inlet temperature. But moment you change it to electric heater, depending on whether it is an impedance type, it's a immersion type, it can be radiant type, times the flux does not relate to the temperature. It doesn't understand that the bulk temperature is going high. So you have to have good controls. You have to make sure the sheath temperatures does not exceed that value, which may cause problem in the reactor. So electrification cannot be looked at just electrifying something. You have to study the whole impact on the process. Perhaps a better example is a CCR platforming, where both feed as well as inter-reactor heaters are of vapor phase. Now you argue that we have been doing vapor phase heaters. Imagine you convert a fuel-fired heater to an electric heater. There is no convection section. There is no flue gas. So if that heater was integrated with a reboiler by steam generated in the convection section, what are you going to do for that? So it cannot be looked at isolation. It has to be looked at the whole unit, and that's what UOP brings in its expertise. How the whole unit gets impacted for normal, non-normal, startup, all these things has to be looked into. So we are currently doing that. We are bringing that forth to our customers, and we're very happy to talk to you about the opportunities of electrifying your process heaters. As I said, there's efficiency is high, 92%, and then because of green electricity, you save on scope 2. More interesting thing is the low-level heat recovery. Typically, we are targeting here the heat, which is between 140 to kind of 70, 80 degrees centigrade. Typically, the temperatures that you see in column overhead condensers, the inlet to the column overhead condensers. So instead of letting that heat go to the atmosphere, can we use it? Can we elevate it to use it in some part of the process? Now, this is not a problem unique to refining, right? We are looking at this problem for the steel industries and other industries where there is a lot of residual waste heat which can be recovered. If you can tap this heat, we will bring our CO2 footprint down. Let's see how we can do that. Okay. There are three things that we are currently looking at. First of them is a heat pump. Second is a mechanical vapor recompression, and third is the organic Rankine cycle. Now, the sketch here, is there a pointer here? Sorry. No. Okay, so you see the refrigerant. So this is kind of an indirect heat pump where you are using an external refrigerant to pick up the heat. The evaporator where you see is actually the process condenser. So it will take that condensation heat and the fluid will vaporize. Then it goes to a compressor. So you are using power here. You are using electricity to elevate that heat. That means you take it to a higher pressure. If you take it to a higher pressure, temperature goes up. And then you have to give this temperature to a process heater. Here is a condenser because the heat pump fluid will be condensing. Now, and it moves in a thermodynamic cycle. So you know that. Now, one of the many differentiators that UOP, being a part of the Honeywell family, brings in is we have special refrigerant, the HFOs. There may be hydrofluoroolefins, hydrofluorochloroolefins, which actually maximize the efficiency here. It's not that you cannot use any other fluid, but this will give you a efficiency benefit in this system, where thermodynamically the efficiencies are low, all of us know. In a mechanical vapor recompression, it's almost the same. The philosophy is the same, but instead of using a refrigerant, you are using steam. So you can generate maybe very low pressure steam against a process condenser, elevate it, and use it somewhere else in the process. So same thing, almost fluid is different. Organic Rankine cycle, you are capturing the heat, but you are not transferring it to the process. You are trying to get power out of it. So organic Rankine cycle again will use the same refrigerant as we have shown, and it can go to one exchanger. It can go to multiple exchanger depending upon the heat levels which are available. I'll show an example at the end. And you have to vaporize this. You have to vaporize this totally before it goes to the turbine, and the turbine will extract power out of it. So higher the pressure at a particular temperature, that means higher the dew point pressure at a particular temperature, greater will be the power recovery, and that is the advantage of the Honeywell refrigerant. Okay, heat pumps. We talked that heat in is basically the process condenser. So you see heat in, evaporation, heat out. Now, it looks simple, but it is not simple. For example, if you consider an existing column, right, you're going to convert the overhead air condenser to a shell and tube exchanger. That itself needs a lot of expertise because one shell may not be adequate to accumulate such huge vapor flows, depending on the duties. What is the difference in carbon number between the two, bottom and the top? What is the difference between reboiler and condenser duty? All of these things are important. All of these things are important to sink it in the process. I will talk in more detail in the next slide where I illustrate this. Temperatures, if you start going to higher temperatures, obviously you will not have high temperatures because you will be capturing it in the process. But if you go to higher temperatures, the fluid changes because the critical temperature, the critical condition of the fluid is important, how close you go to that. All these things is what EOP brings in. It brings in the expertise in the design, in the choice of the fluid, and how you optimize the cycle. So heat pump can, as you see, I'm not going to read this, what is written in the slide, but this objective is using. Now, one of the most important thing is you elevate the heat. Now your process has to have the sink to capture that heat. If I elevate the heat and then I have to put it to another condenser to cool it down, it's not going to work. So that balance, that how much heat is going to peak, how do I fix the compressor coefficient of performance, again is something EOP is bringing into the process. Mechanical vapor recompression. Mechanical vapor recompression, same thing, but steam instead of a fluid. Temperatures, so a very low pressure steam will be about 110, 120. You elevate it to about 250 degrees centigrade. It depends on how many stage of compression you can go. We have had customers in the Far East who have taken this pressure up to about 40 bar because they need it at a higher pressure. So this can be worked out depending on the stages of the compressor. And that heat balance, if you can hit, then this is really a good thing. EOP is doing already this in their propylene recovery unit. We do it in our Oleflex process. Now we are trying to do this more in our other technologies as well. Why do we say that the fluid is safer and reliable? Because Honeywell HFOs, or the fluoroolefins at the lowest.
Banerjee, you have only 2 minutes. You'll have to.
2 minutes? Okay. I didn't know the time is running so fast. So this is the example here. You can see that in case of a heat pump, there's a compressor where the column vapors can directly be taken. This is the direct form of heat transfer. Whereas in a MVR, you are generating steam and then you are bringing it in. So what can EOP do differently? All of you know EOP has high flux tubing. So if I can, being a high flux tubing, cut back on the LMTD, I have to compress less because the hot side now doesn't have to be 25 degrees away from the reboiler outlet. So these are the advantages, and how to sync this with the column. You cannot just come at a point solution. It has to be seen how the column bottom temperature varies and all these things. I'll move because time is less. but we can work with you to sync this to the technology, to the process. We can optimize the column pressures to make sure that we are utilizing all this heat. Organic Rankine cycle, in interest of time, I will move to the last slide, where you see the heat source are at a different temperatures. Now, everything will not act as an evaporator. Something will be used to preheat. You see the sketch. Something will be used to preheat, something will be used to evaporate. And then we extract power out of it. So it is not necessary that it should be condensers. Condensers are good because they have latent heat. You can do it from our product rundown coolers, which has sensible heat, but the quantity is huge because your product rundown are huge. So that power can be easily extracted as a first step. And circuit optimization, whether you use a single turbine, you can use a two-stage turbine to get maximum power out of the loop. So the market drivers are there. I talked through that, and all our esteemed dignitaries have talked about that. We have a comprehensive portfolio Europe is bringing to you in terms of electrification, in terms of low temperature heat recovery, ORC, and of course, EOP with this, you know, the EOP's reliability. And the way we are approaching it, we are talking to every refiner separately, understanding their heat source. We are recommending a study fast to see what is the potential of recovery. Does it pay out in absence of any CO2 tax or CO2 cost? The payback period is much more.
Banerjee, you have to wait.
So last statement. One other thing that I am not able to disclose fully is we are making another, EOP is innovating another technology where we are breaking the thermodynamic barrier of this Carnot engine, because we are bringing a technology which can recover 50% of the heat. I am sure within a month or so, I will have the clearance to talk about that. So that will be a kind of a further step development above the current things which I have shown. So sorry, sir, I may have taken 2 minutes more, but I'm there for any questions which you have. So thanks again to CST and IOCL and chairs for giving, and thanks again to you listening. Thank you.
Thank you for such an interesting year. It's a topic where actually 15 minutes, I believe, is not fair enough. But however, in the interest of time, we'll have to control that. But most of the delegates can connect with you during the lunch period. Okay. So then, okay. The next session that we have is by Technip, innovative approach to revamp of a major cracker. We have Dharmendra Kumar Narang and Maholkar, Sandeep Maholkar, jointly making the presentations, right? Go ahead.
Yeah, good morning, everyone. So this is a joint presentation by Technip and Reliance Industries. I think we have heard about new technologies, new products in the last 2 days. What we bring today in this session is an innovative approach to the revamp of a cracker. So so we don't have a new technology or a product, but what we will describe is what was an engineering approach that we took to revamp it's one of the largest gas crackers in Jamnagar. Okay. So with this cautionary note, let's move ahead. I think we can skip these slides on Reliance. One key point that I would like to highlight here is on the O2C, the deep integration, cost competitive position, and the wide portfolio is what distinguish us. And we are one of the world's largest O2C players operating single largest refinery in Jamnagar. Let's skip this. And yeah, so we've pioneered vertical integration, and the refinery off gas cracker, which I'm going to describe today, is a classic example of the oil to chemicals concept. All right. You'll hear more about the next phase of O2C growth, which we are building new VCM PVC complex. I think at some other point we will explain more on those new projects that we are backing on now. Right. So let's get to the subject, the project that we will discuss is on the revamp of the refinery of gas cracker. The starting point of this was a feasibility study, and the target that was set for us was right from the kickoff meeting to the startup of the plant. We had only 20 months to engineer, procure, and execute this project. The next 3 points I'll explain better in the next slides. So we had certain targets that were set by management. I mean, cracker is a unit that no one likes to shut down. You know, when a cracker goes down, the downstream plants go down. It's the mother of all units. So the right time to shut down cracker is when there is no feed available, and a refinery of gas cracker depends on various feeds from refinery. So in a way, the plant turnaround or the shutdown date was decided by the upstream unit, and the revamp schedule had to match with the plant turnaround schedule. So we had no additional shutdown days on account of revamp scope that was not built into the economics of revamp, which means we had to devise a strategy to implement this project on a fast track basis. While the schedule is critical, the main focus was also that we need to achieve most competitive olefins while minimizing the capex and opex for the revamp. And then, like in a typical project, you had the ROGC turnaround had to match with the project scope, which means there has to be a seamless integration between O&M scope and the project scope. And then ultimately, you need to have flawless engineering and subsequent startup of cracker. Just to give you a plant, the overall perspective of a refinery of gas cracker. So there's a beautiful video on YouTube prepared by Technip, which explains the ROGC cracker. But on the overall, the plot size is about 700 by 500 meters. It can fit about 50 football fields. So that's the magnitude of the plant. It has more than 800 equipment which needs to be checked as a part of revamp in the project. Now, we had certain revamp targets. So ROGC processes refinery of gas, and it was commissioned in 2017, which means it was designed way back in 2013, 2014. So over the last 7 years, the refinery diet changed, the off-gas composition changed. So the refinery off-gas processing had to be revamped to meet the current sat gases and unsat gases availability. And then the extra ethylene was to be made by processing additional feeds in cracker. Some of the product specifications were made stringent. The target was we had to achieve more than 35% ethylene. The propylene was going up by more than 350%, and I think this will be covered in the subsequent slides on why there was a significant jump in propylene. And then we use this opportunity to solve some of the operational aspects and address them as a part of revamp project. So I think I'll invite Mr. Dharmendra to take you through the challenges that we faced in revamp and how it had to be overcome. Thank you.
Thank you, Sandeep, for introducing the topic. I would also like to thank CHT for selecting the paper, the chairperson, Indian Oil as the sponsor, and last but not the least, all the audience still being there at the last day of the session. I will quickly go through the topic. You saw, it's not a small plant we are targeting about. And the reason of presenting it is with all these energy challenges, there may be many opportunities, and many of the clients amongst you will be looking at how do we carry out a challenging revamp. Here we are talking about equipments, more than 450 pieces of equipment to be checked, tags, hydraulics, more than 10,000 lines. It's not a small plant. We are talking about a plant of 50 football fields, touching almost 1,000 control valves, other instruments more than 2,000. So a massive, massive job. We had to identify the bottlenecks, buy as necessary, get them installed, get them going. Time is only 20 months. That is something, a mission impossible to start with. There is something interesting that I would like to share. On top of these challenges, we had some challenge, like we were starting just after the COVID era. Sorry for that. There were challenges because we were starting after the COVID era, the demand was high, the workloads were high. With the Technip organization, one Technip delivery, we put in the resources together from different centers, from different continents together. There were vendor challenges as well, because if you go back 2 3 years, 2 years back, you went to the vendors, most of the vendors will say that we have nothing available, the time is very, very limited, we can't get it. So we did something special there. On top of it, there were construction challenges. Monsoon would come because we were ready to start up in month of October. And before that is the monsoon season, so you cannot put the construction to the last date. Okay, and Reliance had set a stringent target, no shutdown, get it right the very first time. You do not have a way to go back. We did some adequacy check. We asked client, share us all what you have as the data along with all the sampling data, because what we want to do is we want to understand what we did 5 6 years back, whether it works or not, whether it works the way we wanted it to work. We said, give us the challenges. We are not sure we will do everything to fix it, but we will understand the unit so that we get it right. We established unified criteria for doing the job, and most importantly, we made it a single team saying, this is not you, this is not me, this is us together, and only together we succeed. Reliance and Technip, that's the only way, the mantra to succeed on this project. What we did for the new equipment, and what were the kind of new equipment, we are talking about the compressor internals, some reactors to be procured. These are not small pieces of equipment. We had some columns to be procured and all. We said we will make the orders based on the feasibility study. We will get these equipment checked as if these were already an equipment which were there. We will make an adequacy check to see if it works after our design validation. On top, we said we will put up parallel equipment if there are significant modification because of the shutdown window. We cannot carry out the modifications just beyond that shutdown window. So we said we will put up parallel systems because the cost of shutdown is far too big. We did the reuse of valves, the equipments, and we did a lot of reuse, moving equipment from one service to another, because this is a massive plant. We have more than 800 pieces of equipment. Once the things do not work in one service, maybe it can work on the other service. This is to validate the or mitigate the effect of vendors' non-availability. So we did it successfully. On the engineering deliverables, we did something again special. We went with non-finalized PDS. This requires courage from our client. This requires courage from us to go to the market. Maybe we will be wrong, but we had the confidence going together as a single team, we will make it work. We went with a finalized PDS. You can see there were several revisions of the document, but ultimately the things worked. We could reserve the shops, get the things going. Something again on the engineering deliverables. We issued the P&IDs ahead of PFDs. Looks stupid, but sorry, this was the time of the need. So this is something how we approach. We did the equipment things, checking on priority in order to get the things going correctly. And we said, these based on this feasibility study, this is where we expect the bottleneck. Let's try to put them in the right order, in the right sequence. Focus was construction. On the construction, when we were looking at the equipment details, we said, let's focus whether we can construct it and then only issue the engineering deliverables. I give you one example. We had a flare drum with more than 6-meter diameters, 3.5 bar design pressure, so very thin vessel. We were required to cut a 42-inch nozzle in it. You can imagine when you cut a nozzle, the drum will just collapse. If it collapses, all the things go bad. So we did a full deliberation with all the disciplines, how to make it work. And it did work. Something again special, we had hot taps, which most of the clients will say, no, no, I want to minimize. Here we said, no, that's the way to go because of the bigger interest of project. We said, do those hard taps so that we can continue the unit operations while we do the changes. We said we will not modify any foundation. We do not want to dig anything, because if you do anything like this on the ground, then it will make the things very, very bad. Monsoon is coming. You may spoil the other foundations. Do not touch the structure. Build parallel structures. Something most of the people will say, no, I don't want to go. But imagine the cost of non-production that's far above all these little engineering and construction activities. We did a dynamic recalibration. The scope, client had set a target. We did engineering. We saw, oh, it's too big. We may not be able to do it. Let's recalibrate. Let's try to reassign the phases. Let's try to see what we can do, adjust the system engineering, deliver it accordingly so that we can get the shutdown and restart going correctly. You can see lots of issued for construction. People will say that's a bad design, but sorry, this is what was required, and this is what helped us achieve a significant project. Things were adapted, client was flexible, thanks to the client, and I would say this is something you need to consider when you are doing a project which looks very difficult. We did some P&IDs with lots of phasing, lots of colors on it. This was identifying phases so that people can see what needs to be constructed now, what can be put after. We did HAZOPs and all in order to see that all these phasing will work correctly. When we got the things constructed, during pre-commissioning, we said, let's do the clean build, assure that we are requiring minimum intervention, flush the things, secure the things so that you do not require a lot of effort to get it going when the time comes. Just to tell the magnitude of work that we achieved together, we had more than 100 pieces of new equipment which were ordered, modified 150 pieces of equipment, more than 200 pieces of instruments that were modified. We had huge amount of piping. These are not mean numbers, 200,000 inch dia, 300,000 inch meters. These are simply too big numbers. We had more than 500 tines established. More than 10 parallel structures were put. What did we achieve together? Adapted construction of things were done, pre-commissioned, commissioned, tines established, project was done starting from January 22, RFSU 23. This is what we actually achieved. Capacity was reached in December 23. You may say that it's a 2-month gap. What happened? But mind it, this is a unit integrated with more than 20 other refinery units. We need to put this symphony, this raga together so that you bring down shift the loads from one to another. You cannot let the shutdown happen. And it did actually happen. Lots of value improvement things were implemented. New production records were achieved. And I must gladly say, with the sincere discipline of client and the design, the production is sustaining at those high level on a continuous basis. We learned a lot of lesson. I believe client learns lots of lesson, and some of the approaches, that's what we are sharing. Something important on the ESG scorecard in the term of this thing, we had no safety incident. We are talking about heat recovery more than 140 megawatt. Let me tell you, this is below 85 degrees centigrade, 140 megawatts. Let's not look at just energy. What we are cutting off is the cooling water requirement corresponding. This is huge. This is something we were talking about 30, 40, 50. This is 140 megawatts. This is massive. Recoveries were still very high. We reduced the specific energy consumption of the plant. These are actually achieved values. We have achieved a hydrogen production in excess of 240,000 NMQ per hour. We are talking about the biggest hydrogen producer worldwide. Okay, and let's see, this hydrogen is more than the CO2. Because of this, refinery could shut down their hydrogen plants. They could save the CO2 coming out of those hydrogen plants. And let me just go back. Typically, CO2 emissions from a ethylene cracker or ethylene plant is 1 ton of CO2 per ton of ethylene. We are talking about more than 200 tons of ethylene production. CO2 saving because of this, we are talking in excess of 200 tons. Are we talking about a carbon neutral plant today? That's something to look. Furnace run lengths are in excess of 100 days. It's far above. I can't disclose the numbers. NOx, particulates, all were within the range. Thank you very much for doing. I hope I tried to put the time together to do it quickly in that. Thank you.
Thank you for an excellent presentation. It highlights excellence in project management, shutdown management, innovation in engineering approaches. You made a mission impossible to possible through a team approach. Good, very good presentation. The next presentation that we have is from Indian Oil Corporation. The subject is process for conversion of FCC dry gas to high octane gasoline blending components. Presentation by Sandeep T. Bhutia.
Good morning, everyone. I'm Sandeep Bhutia from Indian Oil R&D Center, Faridabad. I will try to give a short presentation on a process for conversion of FCC dry gas to high octane gasoline blending components. Basically, we all know about an FCC unit in a refinery. It's a major refinery workhorse. So typically, FCCs generate around 5% of dry gas in a normal gasoline mode. So, and if you increase the severity of the FCCs in the petrochemical mode, the dry gas content can go up as high as 10 to 12%. So basically, what we are doing with this dry gas, if the FCC is integrated with the petrochemical system, the light olefins in the dry gas can be recovered. But again, the quantum or the capacity of the FCC has to be significant so that the dilute nature of the olefins present in the FCC gas and the recovery is economically justified. So what happens to FCCs that are not integrated with the petrochemicals? So basically what we are doing is the light olefins present in the FCC dry gas goes to our fuel gas systems and we are burning it for heat or power. So basically what we are doing is we are losing some valuable olefins for generating heat and power. So can we have a solution for this? Basically, yes. So we at Indian Oil R&D, we have come up with a process where the process selectively oligomerizes the ethylene present in the FCC dry gas to LPG and gasoline range molecules. The olefin conversion for the process is in the range of 95 plus, and the gasoline has a very high RON of 91. So what the process basically does is the olefins, particularly ethylene, which was having a fuel gas value, has now been raised to a LPG and gasoline value. So these are small units having very relatively lower capex, opex, and refinery footprint. So what does the process does? Basically, the bottom line is the olefins which were destined for burning in your refinery burners has now been converted to a LPG and gasoline fuel. So this is the simplified process flow diagram for the process. So the process takes in the complete dry gas as a feed. The catalyst is a zeolite-based catalyst system, which selectively oligomerizes, aromatizes the ethylene present in the dry gas to LPG and gasoline range molecule. For a standalone unit, we can put up a separate separation section, or else we can also integrate the separation section with other secondary units within the refinery. So basically, if you look at the bottom slide, slide of bottom, you can see that the gasoline is very rich in aromatics, which contributes to the high RON of the gasoline. And the gasoline is also very rich in BTX, so that we can forward again it for BTX extraction also. So as I mentioned that since we are taking the complete dry gas as a feedstock in the process, so since there are other components associated along with the dry gas like hydrogen, methane, ethane, which is coming along with the dry gas. So this slide shows that the other components like hydrogen, methane, ethane are basically inerts in the reacting atmosphere and just runs to the reactor. So they do not take part in the reactions. Light olefins, ethylene, mostly ethylene, and some amount of C3s and C4s that comes with the dry gas. It's get oligomerized to LPG and gasoline. Dienes, if present, can be very harmful to the catalyst and coke up the catalyst very fast. So as I mentioned about integration, this is a simple unit which can be basically integrated downstream of an FCC unit. So we can take the dry gas from the amine treating unit, put up in the dry gas conversion process, and the product from the dry gas conversion process can be routed back to the FCC gas con section. What we are doing is we are sharing the recovery infrastructure from the FCC gas plant, so we can relatively lower the capex and opex of the process. This is a refinery case study for the process. So one of our FCCs operating at 1.5 MMTPA, currently generating around 76 KTA of dry gas. In the conventional scenario, the dry gas is being sent to the refinery fuel gas system. But if you put up a dry gas conversion process and take in the dry gas from the FCC, we will be able to generate roughly around 16% of LPG and around 18% of valuable gasoline. So what we are doing is basically the olefins which were again burning has been valorized to LPG and gasoline. And the second thing is the unconverted dry gas, basically the hydrogen, methane, ethane, which is stripped of the light olefins, can again be recycled back to the fuel gas system. So takeaway, a recovery of light olefins from the FCC, yes, possible with a petrochemical scenario. Again, as I mentioned, these are very dilute light olefins, close to around 3 to 5-8% feed basis. So you need to have a very significant amount of FCC capacity to recover those olefins. And this recovery systems are very capital intensive, energy intensive processes. Again, for FCCs which do not have petrochemical integrations, this is one of the solution, where instead of burning your light olefins present in your FCC dry gas in your process heaters, you can take up with this process and convert the olefins into much higher value chain like LPG and gasoline. So rather than burning your olefins in your burners, it's high time we convert that into a money and increase the refinery GRMs. Thank you very much.
Thank you for doing it before time. The next speaker, we have Alka Sharma from Engineers India Limited. The topic is on utilization of solar energy for sulfidic wastewater treatment and hydrogen production in refinery operations.
Respected session chair, my fellow presenters and dignitaries sitting in the audience, a very good morning to all of you. Today, this is the last session of the conference. From last 2 days, we are discussing lots of technicalities, technologies, biofuels, renewables, CO2 capture. And the beauty of this session is like every presentation is different. It is not connected to each other. So I take an opportunity of being second last presenter of last session. So I would like to start my talk with a quote. It is a line from a poem taken from a very famous poem, The Rime of Ancient Mariners, quoted by, penned by Samuel Taylor in 17th century. It is like this, water is everywhere, but no drop to drink. Water is everywhere, no single drop to drink. I would like to emphasize on this line because my presentation is connected to this. Clean water, basically poet wants to describe the irony of surrounded with water, but there is not availability of clean and safe water to consume. So, I mean, clean water is a naturally available, most valuable resource available on the earth. And I would like to take this message to you. Please conserve it, optimize its uses, and regenerate it as much as you can. So, with this message, I would like to introduce myself. Alka Sharma from Engineers India Limited, and today I'm going to present sulfidic wastewater treatment in refinery operations using solar energy. So before going to the topic, I would like to take privilege to introduce my company, my organization. I belong to Engineers India Limited, a premier engineering consultancy, EPC technology total solution company. It started its journey in 1965 and is still continuing with all uh, great process technologies. Almost more than 70% of the technologies are developed by Engineers India Limited. They are being used in all over India in refineries. We have a strong presence in India as well as internationally too. We are technology-driven organization. We have fully fledged research development center in our Gurugram office. So we have developed more than 70% refinery technologies. They are already implemented and running successfully in the refineries. And we have more than 100 patents filed and granted in together. And despite of refinery technologies, we are also working in renewables, green hydrogen, SAF, and many other non-conventional energy sources and their technologies. So this is the outline of my presentation. First, I'll just touch refinery wastewater and its treatment. Then I'll go to my topic, sulfidic wastewater and treatment and its basics. Conventional system are being used and how EIL's proposed process can replace that, and process development and conclusion. So refinery wastewater, the main sources of refinery wastewater are cooling water, process water, sour water, roughly categorizes as process water are roughly categorizes as desalter water, sour water, spent caustic, and oily wastewater. So the major constituents or contaminants of refinery wastewater are oil and grease, hydrocarbons, sulfides, ammonia, phenols, heavy metals, and dissolved and non-dissolved solid, etc. So this slide shows a general overview of refinery wastewater treatment. So the treatment processes are they are categorized basically in three treatment categories. First is primary or pre-treatment. This is used to remove suspended solids from refinery wastewater using gravity separation, filtration, DAF, equalization, and such kind of technologies. Then come to secondary treatment. This is basically biological treatment, and it is categorized in aerobic and anaerobic processes. And the last most is tertiary treatment. This is the most advanced treatment processes. It is also called advanced oxidation processes. This comprises photocatalysis, Fenton process, electrocoagulation, catalytic ozonation, absorption, etc. So now come to sulfidic wastewater. Sulfidic wastewater is that water which contains mostly sulfides as contaminants, and this is generated in refinery by caustic scrubbing of hydrocarbon H2S rich streams. Basically, for treating H2S from hydrocarbon rich stream, we use caustic solutions. So after caustic scrubbing, there is a steam generated. It is also called spent caustic that contain lots of sulfides. So today my presentation focuses on this treatment of sulfidic wastewater. So these are the characteristics of sulfidic water. COD is in the range of 100 to 200 gram per liter, and then pH is 12 to 13.5, specific gravity 1.1, and then it also contains a small amount of sodium unreacted NaOH. So these are the processes summarized here for sulfidic wastewater treatment. So there are thermal processes, In under thermal processes, we have incineration, wet air oxidation, biological methods, chemical oxidation processes, membrane filtration technology, and advanced oxidation processes. So basically in refinery, wet air oxidation process is used to treat the sulfidic wastewater, which is also called spent caustic. And in this process, basically in the presence of air, sulfides are oxidized at elevated pressure and temperatures to Na2SO4. And then further, they are treated for final disposal. The EIL process is basically, it is also advanced oxidation process. Here we take spent caustic to a photocatalytic reactor where it is treated using sunlight and UV light. And that sulfide is converted to disulfide, and then again that stream is partially regenerated and recycled back to S2S treating section. By doing this, we reduce load to ETP and also save some fresh caustic which is coming to S2S treating section. And there is one byproduct of this process, that is hydrogen, which is a valuable fuel. So the core of technology is photolysis of water. Photolysis is a type of reaction where any large molecule is photo-dissociated in smaller molecules. Basically, in this process, water is photo-dissociated in hydrogen and oxygen in presence of sunlight. So the process is not only restricted to sunlight, it also takes place in presence of UV light, that is also component of sunlight. So, and that process is categorized based on the environment in which it is taking place. So if it is in presence of certain chemicals, we call it photochemical. If it is in presence of biological solution, we call it photobiological. If it is in presence of some electrochemical cell, it is called photoelectrochemical process. And certain photodegradation also take place in photocatalyst. So we called it photocatalytic process. So what is role of sulfides and sulfide in photolysis of water? So this we observed in our study. In presence of sulfide, that hydrogen is liberated and sulfide get oxidized to sulfates and get degraded. Basically, our objective is to oxidize sulfide to for treating the spent caustic, and that is done in this process. What happens in photolysis of water? There is a recombination of oxygen and hydrogen molecules, and to stop that, we need to add some oxidizable agent to the solution, and that reacts with oxygen and hydrogen is liberated. So here sulfides and sulfide do play that sacrificing agent role in the photocatalysis of water. So we make use of that role of sulfides in this process and use this process to treat the spent caustic stream. So this is conventional scheme where spent caustic is stored. Basically, this is like batch. So if I'll take a reference, I'll take LPG treating process where spent caustic is generated, and it is stored in a tank, storage tank, after a batch, where then it is sent to wet air oxidation package and then flash mixing with H2O2. In both the processes, basically it is being oxidized to Na2SO4. Then it is finally taken to for final disposal. In EIL's proposed process, that spent caustic generated in S2S treating section will go to photocatalytic reactor or photolytic reactor, I must say, because we are not using any photocatalyst. So here it is partially regenerated into NaOH, and one more component is also generated during the reaction, that is sodium disulfide, which takes part in the reaction with S2S in S2S treating section. So what we do, we recycle this stream to our S2S treating section, where this again take part in the reaction and reduce hydrogen sulfide to sulfur, and NaOH again react with H2S and form Na2S. Then it is again sent to our photolytic reactor. There that Na2H2 is again converted to hydrogen and NaOH and Na2S2. So like this is a closed loop process where we can save our fresh caustic and also reduce load to ETP. And after 2 to 4 cycles, as I earlier mentioned, this is a batch process, we can finally send to spend caustic to ETP. This way, we are saving fresh caustic as well as reducing load to ETP. These are the reactions. As I mentioned, sodium sulfide, when reacts with water in presence of sunlight or UV light, it forms Na2S2 disulfide, NaOH, and hydrogen. That Na2S2 again take part in the reaction with H2S and form NaHS and water. That NaHS again is a photolytic solution which photo dissociates and form hydrogen. And Na2S2 when reacts with H2S it form NaHS and sulfur molecule. So this way it is enhancing basically H2S treatment and also treating sodium sulfide. If we'll compare O2 requirement between conventional process and EIL's process, we find with your conventional process we require around 2.5 moles more oxygen, while in comparison to our photolytic process. One positive point is that oxygen is in situ generated by dissociation of water molecule in the system. So we don't need to add any extra air in the system. In the presence of sunlight or UV light, it photo degraded into hydrogen and oxygen reacts with sodium sulfide and hydrogen liberated. So these experiments we have done in our lab. So this is our photolytic reactor where we have done experiments for different light intensities using UV visible high pressure mercury lamp. And we have used synthetically generated sodium bisulfide aqueous solution. And we have done proof of concept, and that idea is established, it is achievable. This is our full-fledged lab skill setup. This is a typical case study of the feed is actual feed from a refinery, where I'm showing from feed how much hydrogen is being generated. So basically what happens, first feed goes to photolytic reactor, then it goes to H2S treating section, then again photolytic reactor. In one recycle, there is if it is 8,000 kg of feed, with having around 200 of Na2S, it generates around
Madam, you have 1 minute.
16 kg of hydrogen and reduces to sulfur 95 kg. So in summary, I would like to say that EIL proposed process is a very good process to convert to reduce sulfides to final products for disposing of, which reduces ETP load and also reduces makeup caustics used in caustic scrubbing section. So I mean maybe in future this process will have more relevance when it comes full-fledged after being tested in pilot scale. So like this, I would like to conclude here. Thank you for your attention and time. Thanks a lot.
We come to the last presentation of Suhas Nair. Request you, Mr. Nair, to take finish it in 10 minutes. Okay.
Hello. A very good afternoon to the respected chairpersons, Sri Panikar sir and Sri Kaushik sir, Good afternoon to all the dignitaries, delegates, and speakers on the dais of the dais. So from last 2.5 days, we were discussing on various aspects covering up on the reductions of CO2s or CO2 emissions. So with my presentation, I'll also cover the same topic, how chemical treatment programs can contribute in reducing the carbon emissions and fuel cost. Um About the organization, DOF Kettle is established in 92. So we are a 32-year-old company growing faster in the specialty chemical division, not only for the refinery or petrochemical, but for the complete hydrocarbon sectors, start from crude oil exploration to the aftermarket segments. We also means during last 32 years, we had acquired like more than 15 organizations in the hydrocarbon sector, serving for the hydrocarbon sectors with specialty chemicals, also diversifying into drones as well as for the AIML segments and aligning it with the refinery and hydrocarbon applications. So the agenda of my presentation will be on the fouling controls in the hydrocarbon sector, that is refinery as well as petrochemicals. So what are the contributors for the foulings in the refineries or petrochemicals, and how DOF Kettle contributes in reducing the fouling and controlling on the CO2 emissions, the product differentiators, what we deliver. So carbon penalty means one of the major energy consumers in refineries are the preheat exchangers or the furnaces. So when the exchangers gets fouled, it demands for a higher fuel consumption to meet the energy requirements that finally end up in contributing more for the CO2 emissions. What are the impacts of fouling? So fouling normally leads to energy loss, operating at lower temperatures. So to meet the requirements of the energies and heat, we increase the fuel firings, and thus also our run lengths are reduced because of the foulings. This also leads to throughput loss for the refiners or the operators, as well as increasing the CO2 emissions. Now, we all know what are the normal fouling contributors in an hydrocarbon sector. It could be operational factors, which includes design limitations, flow restrictions, or the exchanges or the poor operation separations, what happens across the refineries. The other major two factors are organic foulings and inorganic foulings. Organic primarily because of the asphaltenes, wax, gums, which is because of the type of feed we process. The inorganic foulings also is contributed because of the corrosion products or the various metallic salts which comes along with the feed. Even the solids or the silts which is coming as a contaminant into the feed. So these are the major contributors of fouling. In a refinery, major areas where fouling impacts on the higher fuel consumptions are the crude distillation units or the vacuum distillation units, hydrotators, FCCUs, whisk breakers, and delayed coker, mainly on the furnaces of the whisk breakers and delayed cookers. So here I'll be focusing on the crude as well as the delayed coker fouling controls. So in a crude distillation unit, the preheat exchanges, whether it could be a cold preheat exchangers or the hotter sections, which normally goes for fouling and which reduces your throughputs, means you are forced to take shutdowns because you are not meeting the energy demands. You may be forced to increase the fuel firing, thus increasing your OPEX as well as increasing on carbon emissions. So what normal approaches we recommend to our customer is like we provide comprehensive solutions wherein we can recommend certain products which can help to reduce the amount of inorganic foulants getting into their systems and giving a better separations. We provide multifunctional anti-foulant solutions. We also support our customers with simulation models which can predict fouling and how it can be mitigated. So this is a typical inorganic organic fouling which happens in a refinery wherein the with various crudes or high asphaltenic crudes, the asphaltenes gets destabilized when it gains heat through the preheat trains and finally precipitates out, leading to foulings, and wherein means even the metals which comes along with the crude also contribute in catalytic coking of the either the exchangers or in the furnaces. Tofketel, as a solution provider, chemical solution provider, to mitigate or to control the inorganic fouling, we recommend for reactive and adjunct chemistry, which is an innovation which we had done. It's a aid along with the demulsifier, which we recommend for the desalter treatments, which helps the refiners to process tougher, heavy crudes, although with higher amount of solids or sludge, and effectively giving a separation, thus reducing on the oil slippage which happens to the ETPs, which leads to generation of slops. It also helps to reduce the amount of solids or the contaminants which escapes from the dissolvers and gets deposited in the downstream exchanges, leading to foulings. This is a case study of this particular application, which help to control inorganic fouling in one of the Asian refineries, wherein they were facing a lot of fouling issues, inorganic fouling issues, because of high filterable solid contents. So you can see with the treatment programs, the oil slippage has reduced considerably, which reduced slop generations. Also, it also contribute to improve the heat integrity. So if we, the graph shows how the furnace inlet temperatures or the drop in the furnace inlet temperatures has reduced from 10 degrees to 2 to 3 degrees, which contributes significantly on fuel consumption cost savings. We also can attribute this key. This will save significantly on the tonnage of carbon dioxide emissions, which happens because of the excessive fuel firings. Touching upon the organic fouling control in the primary units or the crude units, we normally provide with various chemistries, primarily on the asphaltene dispersants, various multifunctional antifoulants. Also, we provide to the customers as per their feed quality requirements, to means whatever their foulants or the type of foulants they face. So it could be a combination of asphaltene dispersants, metal chelators, or antipolymerants. So depending on the feed qualities, depending on the data we evaluate, we provide solutions which can help them to reduce on the asphaltene precipitations. This is another case study wherein a customer, an Asian customer who was facing considerable fouling because of the organic matter or the asphaltene depositions while processing some high asphaltenic crudes. So wherein with the chemical treatment or with an effective anti-foulant treatment program, they were able to improve their furnace inlet temperatures by almost like 40%, which contributes significantly on the in terms of savings on fuels as well as reductions on the carbon emissions. I'll also cover on the coker furnace foulings. So many of the operator refiners face issues of lower run length of the coker furnace, leading to operational challenges wherein they are supposed to cut the throughputs. So as a chemical treatment provider, we provide treatment programs to control their furnace foulings in the cokers. The feed qualities or the feed properties which normally influence the foulings in the cokers are the asphaltene, CCRs, metal contents, and major impacts on the refiners because of the furnace fouling as reduced run length, higher fuel consumptions, reduced CVITs, increased coking or decoking costs. So the conventional methods, what refiners normally use is steam air decookings, or could be a mechanical cleaning or a pigging or an online spallings, which takes considerable amount of time. You are losing on your throughputs, you're losing on your GRMs. Another approach what we recommend is an antifoulant treatment, wherein we provide multifunctional chemistries, which helps to improve their run length. We also do provide an AI model to optimize on the furnace run length. It's called Cokenil. The product which we provide as an fouling control is a combination of
Mr.
coke
Subhas, you have
inhibitors.
to 1 minute. Okay.
Okay, the last topic I'll touch is on the ethylene cracking and cooking controls. So typically in a furnace, in the ethylene furnace, the cooking happens because of either catalytic or pyrolytic cooking. Um, sulfur or DMDS as a conventional method is used to control or the passivate the active nickel sites, which reduces the rate of cooking and control the catalytic coke formations. As Dorf Kettle means we believe in innovations and indigenizations. So as an Dorf Indian company, we had developed an alternate for the DMDS, which we traded as a trade name is Sulsafe, which helps or to replace DMDS, providing at par performance with DMDS, providing sufficient sulfiding of the furnaces, thus reducing on the catalytic cookings. So some of the benefits is listed like it also helps to improve the yield, extend the furnace run length, reducing on the carbon CO2 emissions, improved coke controls, CS2 generations, and many lists. This is one of the case study of a Linde licensed plant wherein because with our chemistry we were able to improve the furnace run length by almost like 20%, thus reducing on carbon emissions and reducing on the fuel cost. So my conclusion is like fouling is one of the biggest contributors for increasing the furnace firings, leading to high fuel consumptions and increased carbon dioxide emissions. Inorganic and organic foulings also means contribute significantly for such foulings. We as a treatment providers can get associated with our customers to improve their efficiencies, energy efficiencies with our technologies and models which we support to analyze this. Thank you.
We are absolutely running out of time. We have about 5 minutes till 1. So we'll take about 3 to 4 questions, if it's okay.
Yeah, my question is to Mr. Sandeep, and this is regarding revamp of your unit at RIL. It was really a major job which you have carried out. I just wanted to know, you have mentioned more than 500 tie-ins were there. So how much you did while plant was running, and what was the percentage during the shutdown? Can you just tell me?
Okay. About 30% of the times were like hot taps, and rest were done during the shutdown.
And what was your number of days for shutdown?
The number of days was 30.
30 days you have completed
Exactly.
everything.
Hold on. I hope you noticed that we said we were doing some of the things parallelly. So some things were built before, some things will be built after. But to establish the time so that you can bring up those facilities which are built later online was completed. And we had to do the full scope analysis in order to see how we will survive during the intermediate duration. And we did HAZOPs and all. It was really a challenge.
Okay, so shutdown window was just 30 days.
Correct.
Oh, great. Thank you. Thank you.
Welcome.
Mr. Banerjee, thank you for the refresher on thermodynamics. I, for one, was in need because it's been a long time since I looked at the Carnot cycle or Rankine cycle. I fully respect the contributions UP makes to the improving energy efficiency of refineries. I don't want to steal any of your thunder. However, there was one slide, one chart that you presented on the CO2 pricing anticipated in Europe that caught my attention, and I'd like to share a European perspective. Because if we see a chart with the CO2 price going up to 150 or 200 euros a ton, well, choose your expletive, but this is really serious, right? Certainly when we're in refining, we say what's going on, and that's going to be extremely expensive, or conversely, it's a great basis to justify energy improvement. Now, the comment I'm making is, what is a CO2 price? It's not a tariff set by a government or something like that. The CO2 price in Europe is what the market expects is the cost of CO2 remediation in the future. And that is a price that depends on technology, what technologies are available, and some are cheaper and some are more expensive. And it is a balance of supply and demand, what credits are available or how much reduction is required. I'd like to add, so what does that mean actually? What I would encourage is everyone is to read the Bloomberg report, because that pricing is underpinned by certain assumptions, certainly by a policy framework in Europe. As carbon pricing comes to India, that policy framework will be quite different, I'm sure. Also, so you can get into a frenzy and panic and say, I have to pay 150 or 200 euros a ton. Well, perhaps in India that will be different. We do need, it would impact Indian producers through CBAM mechanism. If you're producing products with the implied CO2 content and you're importing that or exporting that to Europe, then there is the CBAM, is the carbon border adjustment mechanism that says you have to pay for that CO2 if you did not reduce it in India as the products enter into Europe. So I would caution everyone here is not to get into a frenzy and to worry about 150 or 200 euros a ton on CO2. It depends on the policy framework that you are implying here.
Yeah. Can you hear me? So yes, we are aware that this policy is continuously evolving, right? And it changes. So that's why the references, you have also seen a dotted line, right? There is an expectation, but you are right. As it evolves, there may be several taxes which can be removed or added. So right now, as I said, we don't have any CO2 price in India as such. Right now, maybe people have their internal calculations based on you know that there are various methods of doing this calculation. In Europe, you have the Reddit and all those things. So we are keeping a watch on it, and we are not saying that this will go on in a continuous manner increasing. So as it evolves, we will like to know that how the prices go up. But as on today, as you know, at least in US, $80 per ton, that prevails. So more or less, Canada is about 69. So around about 100, it's still there, which is prevailing. So.
I agree. The experience currently in Europe is 100 is about a threshold.
Correct.
But in the meantime, I would say stay calm, reduce your energy, and continue to operate.
Yeah, good morning. This is Sudeshna Datta, Senior Projects Manager working with Refineries Headquarter, Indian Oil. My question is to Narang sir. Congratulations on the record achievement. Just wanted to understand what kind of novel construction methodologies you must have adopted that you could achieve such a record, apart from modularization, of course.
Incidentally, we didn't do any modularization. Okay. What we did, there were some keys. Like we said, certain things we will not touch. For example, we will not touch with any foundation. If we require to make something, create the foundations parallel. Do not tinker with any existing structures. Do not load them. These were the little steps. It's all about innovation. That's exactly the reason we named the title as Innovative Approach, because it was not going to, let's say, change everything, because else we would not be on a proven path. So we were making these little corrections to minimize the risk. We said we will not try to touch much things underground. Okay, try to be sure that you can construct, do the parallel structure. I can give you one example. We had a column where we could do with the modifications inside, but we were considering it may be risk to do it. We said, let's build a parallel column together. Because if we build the parallel column, we can lay the foundations. We ordered the column in advance. So we could tie in it like this. We were not making huge changes because else we would go on the unproven path and we had no chance to fail. We had to make it a success.
We'll take the last question, one last question only.
Do we have a last question? Show of hands, please. Anyone?
I think we can conclude then.
We're done. Well, thank you so much, ladies and gentlemen. May I please request you all to put your hands together and thank our esteemed speakers here on the dais. May I please request you all to come together for a group picture. Keep the applause coming and do not go anywhere, ladies and gentlemen. Please remain seated. We are not going to take much time. This is the last session. We are going to wrap the session. But before that, we'd like for all of you to remain with us in this very hall. Thank you. Please remain seated while we take a moment to acknowledge the amazing minds that we have here on stage with a round of applause, of course. Thank you so much. And with that, I'd like to request Mr. Prasad Panikar to kindly step forward and present mementos to our distinguished speakers, starting with Mr. Somendra Banerjee. Thank you, sir, for sharing with us your valuable insights. Please put your hands together. Keep the applause coming, ladies and gentlemen. A humble request, do not leave the hall yet. This is our way to thank people who put this phenomenal show together. Thank you. Thank you so much, Mr. Dharmender Kumar Narang, for being here with us and sharing your valuable inputs. Mr. Saneep Mahulkar, thank you so much. I don't hear an applause. Come on, everyone. I now request Mr. Kaushik Singha to kindly step forward and present mementos to our other speakers. Mr. Sandup T. Bhutia, thank you so much. Ms. Alka Sharma, thank you, ma'am, for being here with us this morning. And thank you, Mr. Suhas Nair. I now request Mr. Alok Shukla, Director R&D, to kindly join us on stage and present a memento to our extremely charming moderators who are not smiling at the moment, but I'm sure this is going to add a smile to their faces. Put your hands together. Big round of applause, everybody. One group picture with everyone together. Everyone please step forward. I will not ask you to wait any longer, ladies and gentlemen. Just about 5 minutes while we wrap this fantastic event. But take a moment to applaud. Come on. Thank you. Thank you, everybody. Thank you so much. Well, on the... Gentlemen, may I please request you to kindly remain with us for 2 more minutes? Thank you so much. Well, with that, ladies and gentlemen, as we conclude the 27th Energy Technology Meet in Bangalore, I'd like to take this opportunity to extend heartfelt thanks on behalf of IOCL and CHC to all those people who made these 3 days incredibly remarkable. Can we take a moment to put our hands together and thank them all? Everyone, please, big up. Round of applause. Thank you. We've seen some outstanding presentations that have broadened our perspectives and also witnessed some impactful, insightful panel discussions. Now, aside of these sessions, we also had an incredible networking opportunity that allowed us to forge connections, share knowledge, and strengthen our community, which is very important. Thank you all once again for making this an incredible experience for all of us. We really look forward to welcoming you all again next year. Until then, I'd like for all of you to stand up and clap and thank everyone behind this incredible, massive, successful event, the 27th Energy Technology Meet. Come on, everybody, put your hands together. Thank you once again, ladies and gentlemen. My name is Archana Deshmukh. Please take care until I see you all the next time. Let's continue building a sustainable future together. Thank you. I now request the CHT team to come onto the stage and enjoy their moment of glory for a group picture. I request the Center for High Technology team to come onto the stage. Thank you once again, ladies and gentlemen. Enjoy your lunch. We will see you all again next year.